So welcome everyone to our Routing Switching and Essentials ITC course, our class meeting for week of 1017. Apologize again for having to have class this week on a Tuesday, but I appreciate everybody being here and showing up. We're going to talk today about dynamic routing. We've already discussed routing with static routes and how useful static routes can be. We talked about how sometimes you don't need a dynamic route. Sometimes, for instance, can you remember one of the use cases for a static route? What do we say was a good use case for static routes? Anybody? Oh, you're not like my students, are you? Okay. So a good use case for a static route would be a stub network. Okay, so static routes are great for stub networks because remember, that's a network that only has one path out. If it's never going to have more than one path out, then they are extremely good for static routes are good for that. Another good thing for static routes are small networks. Okay, so stub networks, small networks. You need a simple network, or if it is a simple network, those are all good for static routes. Static routes are better than dynamic routes in one way, too, because they're more secure. If you use a static route, you know exactly how traffic is going to flow in your network. However, static routes do not work in large networks. They simply are not feasible. They are way too much administrative overhead, and so we have what are called dynamic routing protocols. These protocols allow routers to share information about their connected routes, and that's what they typically do, is connected routes. Now, BGP is a different beast. It can do all kinds of weird things, but here are some different types of protocols. We've got interior gateway and exterior gateway protocols, and to understand these, I really need to give you a definition. There is a thing called an autonomous system, and this is a group, boy, that was terrible. A group of routers under the control of a single administration running the same interior gateway protocol. So in other words, for instance, imagine that you've got 6 routers sitting inside of your network connecting your sites that are just your company. So in other words, you control every bit of it. Those routers could all run OSPF between themselves. And OSPF V2 or 3, either one, would be able to run inside of that because they're called interior gateway protocols. So IGPs work within autonomous systems. Exterior gateway protocols like BGP work between autonomous systems. So BGP is the protocol used to keep the internet going. It is the internet protocol. Let's see if I can find it. Let's see. I'm going to show you the BGP route table if it'll pull up here. Okay, Dan asked you a question. It says, printers and servers should use static IPs. Do they need static routes? No, they do not. They do not need static routes because remember, the routers are handling all of that information. Good question. Notice here, folks, the number of ASs and autonomous systems in the routing system is 58,993. As of today, 10/17, or excuse me, 10/10/17. Oh, excuse me, 10/17/17. There are 685,182 prefixes inside of the BGP routing report or routing table, and they're aggregated down to 378,677 routes. So that gives you an idea of the number of routes in the route table. This is what makes the internet go. This is how ISPs send information between one another. This is also why if you mess up BGP and accidentally download the information into your routers, that is the entire BGP prefix table or route table, you're going to destroy that router's ability to do anything because your router probably doesn't have the capacity to handle it. But BGP goes between autonomous systems. We are going to do mainly this chapter, and later on we'll look at BGP, but this chapter we're going to look at a very simple interior gateway protocol called RIP. RIP, Routing Information Protocol, has been around for a long time. In fact, let's see here, I got to find it, BGP. RIP version 1 came out, what, 1989, somewhere in there, 1988. So 1988 was the first version of RIP v1. RIP v1 is a classful routing protocol, and that means it does not carry, and I'm going to give you two other definitions here. So IGP, or interior, golly, I have completely gone brain dead. Getting hit by trucks, tough. All right, interior, started on. Still started on. Interior gateway protocols. Route within an AS. Exterior. Route between ASs. I'm going to write that out. Okay. Now, inside of each one of these types of protocols, there are classful protocols, classful routing protocols, and there are classless. And what you will learn about these is that a classful routing protocol does not carry subnet mask information in the route updates. In other words, it assumes a classful mask. So class A, class B, class C. Classless carries subnet mask information in the route table updates. And then that way they can actually use VLSM. So classless supports VLSM. Whereas classful does not support VLSM. RIP v1 was a classful routing protocol, so it did not carry subnet mask information. And I might want to actually spell that correctly. RIP v2 is classless. It has the ability to carry that information inside the route table updates. So when we look at a dynamic routing protocol, some different things it must have. It must have the ability to share route table updates, and by doing that using some type of structure that allows it to do a routing protocol message, it has to have some type of table to store the information from those messages. So either be a route table that's in RAM, a topology table in RAM, a neighbor table that's in RAM, and then it has to have an algorithm to determine what is the best route. We have 4 dynamic routing protocols, a couple different things, and that the algorithm is how we find our metric. And the metric, again, is how the best route is found. We discussed, I believe, last week, the difference between a metric, okay, and administrative distance. We talked about how if we were going to choose between 2 or 3 different Mexican restaurants for lunch, we would use our metrics. So cost, quality, okay, distance from work. Those could be all metrics of how we pick one Mexican restaurant from another. So metrics are how you find the best path within a protocol. Administrative distance is how you find the best route between protocols. And we made a mention that for whatever reason, EIGRP has a metric, okay? Anybody remember what the metric for EIGRP is? I don't even know if we talked about it, but it's bandwidth plus the sum of the delays. Okay, that's the metric. So if I had a route or multiple EIGRP routes to the same network, the metric that would be used to determine which one of those would be placed in the route table is this bandwidth plus the sum of the delays. We'll talk more about that as we talk about EIGRP. But EIGRP has an administrative distance of 90. OSPF, another interior gateway protocol, has a metric that is cost based upon the speed of the link. It has an AD of 110. So if we had a network, let's imagine the network is 192.168.12.0/24. So that's the network we need to find a path to. And we had multiple paths from EIGRP with EIGRP to this network. The first thing we would do on our router is determine the best path using EIGRP's metric. If we had multiple paths using the OSPF, notice we're running both protocols. So you would use OSPF's metric of cost to find the best OSPF path. Then, when you compare these two, you have to make a decision about what's going in the route table. And it would be the one with the lowest administrative distance. Now, what if we put a static route in here? Anybody remember what the AD for a static route is? Anybody remember? Reba, you can't hear me? Can everybody else hear me?
Yeah, Kelly is 1.
That's 1. Yep, exactly right. Static routes have an AD of 1. So if we had 3 routes, one via static, one via EIGRP, and one via OSPF to this network, the static route goes in the route table because it has the best administrative distance. So that's an important thing for you to remember and understand the difference between a metric and the administrative distance. Okay. Any questions about that?
I have a question. Shouldn't the two be existing or?
Say one more time.
I mean, if you have let's say a RIP or OSPF and then you have a static route, won't the two be existing although they're the same path? Will it delete the OSPF?
Okay. Good question. Okay. It doesn't delete the OSPF route. It just doesn't place it in the route table.
Okay.
So imagine this. Let's imagine we did have these 3 routes. Okay. And this one was in the route table, but this route went down for some reason. So we lost this route. This route would then be placed in the route table because the router would go looking for another way to get to this network. It would find that it had these 2 routes and it would place this one into the route table. If this route came back up, then it would replace this route. So they don't go away, they just don't get placed into the routing table.
Is that what we mean by floating?
No. Well, yes.
Or backup?
Yes, that is what we mean by that. Because so let's imagine we had a static route and we gave it a metric of 50, okay, which really gives that metric 50. What would happen is this route goes in the route table. This one is not in any route table, but it's still sitting there. Okay. So if this goes out, this route would take over. If both of these go out, then this route would take over. If all of these, then this route takes over.
Okay.
So the routes are still there, they're just not placed into the route table. We're also going to learn about EIGRP and OSPF. Both have the ability to have additional routes, especially EIGRP is what's called a feasible successor. It can have a backup route in the topology table that can immediately go into the route table and not require recalculation of the route table. So that is how those routes can be eventually placed into the route table. that make sense, Dan?
Yeah.
And that is that would be a backup route. An example of having a backup route.
Right.
We talked about static route uses. We talked about disadvantage and disadvantage. I think you've seen this 3 or 4 times now, so I would give you a little warning there. Just let you know it's probably important. This would be a nightmare with static routes. Okay. This would be even worse. Is it impossible? No. You could do it, but it would not be something that would be very resilient, and it wouldn't be able to adapt to change well. So we're going to look at doing some dynamic routing protocols. Now, some of the advantages. It is suitable in larger topologies. You can make networks of 50 routers, 100 routers, and configured correctly, there's no problem with using a dynamic routing protocol. It automatically adapts if there's an issue with the topology or if the network itself changes in some way. Route goes down, there's another route that will be picked up and put into the routing table based upon the metrics in use. There's some disadvantages. It can be more complex to implement. It is less secure because you don't always know exactly how your traffic is moving when a link goes down. It definitely takes more resources on your routers because the routers have to run the routing protocols themselves. So they send those route sharing mechanisms across the links. So you've got some bandwidth being wasted on those route table updates. The CPU has to run the algorithms to figure out what the best routes are. There has to be a routing table. For some of these protocols, there's also a topology and a neighbor table, as you will learn. So, suitable for multiple router topologies, for dynamic routing. Adapts to change and reroute when possible. Okay. Easy to implement in small network would be static. Requires more CPU and link here. And route to the destination is always the same would be static. So I should get those right. So, how do I configure RIP? It's extremely easy. All right. What you're going to do is on the router, you're going to go into global config. You're going to do router RIP. Then you're going to put in network statements for each one of the networks that are on the directly connected interfaces. So, router RIP, we're now in config router mode, which is the routing protocol configuration mode. You then add in the network statements. So you're going to put in network and then the actual network that you want to route for. In the case of each one of these, you would put in the 1.0 network and the 2.0 network on R1. It is very important that you realize this. You only put in network statements for your directly connected networks. Do not put in statements for anything that you're not directly connected to. So R2 is going to have 3 statements, 2.0, 4.0, and 3.0. And R3 will have 2 statements, 4 and 5. Once this is configured, they will start sharing information with one another. So very simple configuration. Here's how you advertise your networks. Network 192.168.10. Notice you don't even have to put subnet mask information. It will actually, right now, since we haven't changed it, we're running RIP version 1. If you just do router RIP, you're running version 1. You will have to issue the version 2 command in order to begin running version 2. But right now, it will assume a classical mask, which in this case, it actually is using classical mask for each one of these subnets or networks. Okay. If you want to verify routing, show IP protocol. It'll tell you what routing protocol is running. It's also going to tell you what version you're doing with RIP. So you're sending version 1 and receiving 1 and 2. Once you go to version 2, it will send to receive 1 and 2. This is important because right now automatic network summarization is in effect. As long as this is in effect, even if you're running version 2, RIP will work like a class full routing protocol. In other words, it will summarize to a major network boundary. We'll show you how to fix that. And then you can see show IP route, begin gateway, you're going to see your RIP routes, which is the R. Neat thing is when you do a show IP route, it will tell you what R is and it's RIP. So, no problem there. If you want to enable version 2, you just type V2. Okay. So you go in and say, notice here, we're saying it's sending 1, receive 1, 2. We're going to go in and do version 2. You'll notice now once you set version 2, it's actually going to only send and receive version 2. Send to, receive to. Now, once you do that on R1, it will no longer talk to R2 until you convert R2 to version 2. Well, actually, it would receive, no, take that back. R2 would get the information from R1, the R1 wouldn't get R2's information because it's only receiving 2. Okay. So pretty easy. We're going to use version 2. We should almost always use version 2. In fact, real world, we're not going to use RIP at all. But it's just using the protocol to teach you how to use this. Once, show IP protocols. If you want to turn off automatic summarization, there's a simple command called no auto summary, and that will disable auto summarization. Not a big deal in this network, but if this was 172.16.1.0/24, and this other side over here was 172.16.2.0/24, if you had automatic summarization in effect, R3 would advertise the 172.16.0.0 network, and R1 would advertise 172.16.0.0. So the summarization is important. And again, let me kind of show you that. So imagine we had this network here, and we had on this Ethernet on this side, the 172.16.1.0/24 network. And all the way over here on R3, you had 172.16.2.0/24. If automatic summarization was in effect, R3 would actually advertise and say, hey, I know how to get to the 172.16.0.0/16 network, and would advertise that over to R2. Okay, so there's R2 sitting in the middle. And then on this side, this router here is going to advertise, hey, you know what? I know how to get to the 172.16.0.0/16 network. And guess what? R1 says this network is 1 hop away, and R3 says this network is 1 hop away, because it's summarized to a classful boundary. R2 would then have 2 routes in its route table via RIP, one that goes over here and one that is over here, because they're the same distance, so we'll try to load balance across there. This is all fixed when you do no auto summary, because at that point, instead of advertising the classful network, it advertises the actual subnet mask information. And it would advertise the full network or full subnet instead of the classful summarization. Does that make sense? Because that's a very important point about summarization and classful versus classless routing protocols. Dan, you're asking about double static routes. Oh yeah, we always do double static routes if you want to. So you can do a static route. Yeah, talking about here, you could definitely do static routes here. I mean, this network, honestly, you could use static routes as easy as anything else, because R1 could do a default route to R2, R3 could do a default route to Route 3, excuse me, R3 to R2, and then you could do 2 routes on R2. But we're wanting to learn dynamic routing protocols here. So, hey George. So, another item that is interesting when we talk about routing protocols is every 30 seconds by default, RIP sends its entire route table out, all the interfaces that are configured running RIP. So on R1, every 30 seconds, the entire route table goes out. This gig 00. It also goes out as 000. The problem is there's nothing over here on gig 0 that needs to get that route table. Same thing over here on R3. There's nothing here, and there's nothing on gig 0 of R2 that needs to get. There are no RIP routers over here. So what you can do is you can configure a passive interface. When you do this, the interface will no longer send out RIP route table updates. It will listen, but it will not send out. So you're reducing the amount of wasted bandwidth, wasted resources, and you're reducing your security risk, because a hacker sitting out here on this link couldn't sniff your RIP routes that are being advertised. So passive interfaces need to be set on any interface that is not connected to another RIP device that you don't want updates to go out. And by the way, passive interfaces will be the same with OSPF, EIGRP, and RIP. They're the same concept. Now this is a really cool idea here. It's something that's neat. It's called propagating a default route. This is the internet. This is your internal network. You want the R3 and any host out here to be able to get all the way to the internet, but you don't want to have to put a static default route on each one of these devices and say, okay, R3 send it R2, R2 send it R1. We're running a dynamic routing protocol. I don't want to have to put in static routes on all the routers inside my network. Now this network wouldn't be bad because it's 3 routers, but what if you had 50 routers? By the way, you couldn't have 50 routers RIP because it has a maximum hop count of 16. So really 15, so 16th is a non-reachable route. What you can do is you can go to R1 and put a default route going out to the internet. So we're going to do that first. I'm going to put a static route in here, IP route quad 0, S001, and then next hop. This is a fully qualified default route. We're going to router RIP and type default information originate. You only put this command on the router that has the default route. We used to call this the magic dust command, and it is magic dust, but it only goes on the router with the default route. At that point, that router will automatically advertise inside to the other routers a default route, and that route will show up like this. You will get a RIP, an R star. In other words, it's a candidate default route. That's what the star stands for. And it tells you this route was learned via 4.2. This is actually R3, I believe. Yeah, this is R3. It was learned via 4.2. So this route is propagated from R1 via RIP to R2, and then R2 via RIP to R3. So we put one default route here and use default information originate, and it's being advertised inside or propagated inside to all of our other routers running RIP. Saves you a ton of time. You'll notice it was learned by RIP, so you know it's been propagated into RIP. Now, let's see what time. All right. Route table entries. When we look, this is our reference topology here, so we've got a couple different topologies, but we'll look and see our different routes. When you look at R2, you know it's going to have at least 3 connected routes. We're going to look now at R1. R1 has our static default route. It has its connected routes, which would be here, here, and it should have a connected route to the internet. It then has a large number of RIP routes that it's learned. So it should learn 1, 2, 3, 4, 5 RIP routes at least. So let's see, 1, 2, 3, 4, 5 RIP routes, which it does have. So it's learned all of those via inside of here. All right. And that is how we can look at the route table entries. Now, we have to look, we're going to look at the route tables, and we're going to look at the different types of routes in the route table. And be aware that originally it was implemented with classical routing scheme, though now classical and classless are built in. So we have directly connected routes. It shows you a route source, routes you're going to, and how you get there. So that's pretty easy. If there's a destination network, it tells you your source, the route you're going to, where you learned about it, and the interface you learned it on. Okay. So here we see these are static routes. D is EIGRP. You're going to learn that that is because it uses the diffusing updating algorithm or dual algorithm. OSPF is O, and R is RIP. And so this you can see how you learned it, destination, outgoing interface. Good to know that. If it's a remote entry, it's the source, destination network. The AD is in the first part of the brackets. The metrics, the second part of the brackets, where your next hop is, how long you've known about the route, and then the outgoing interface. Okay, so that's how a route table for a remote entry looks inside the route table. So we have different types of routes inside the route table. Now, this is a little confusing, but bear with me here, okay? An ultimate route is a route that has an outgoing interface or a next hop address, okay? So an ultimate route is, it has an outgoing interface or a next hop or an exit interface. So next hop IP or an exit interface. So when you look for an ultimate route, it has to have that next hop or an exit interface, one of the two, okay? So looking at our different ultimate routes, these are ultimate routes because they all have a next hop or outgoing interface. A level 1 route is a route with a mask that is equal to the classical mask or less. Now, how can it be less? There's a thing called a supernet. Supernets are defined by what's called summarization. We talked about summarization in Introduction to Networks. So a supernet is a group of summarized networks. So that is a layer 1 route. There can be layer 1 ultimate routes, and that is a layer 1 route that has a next hop or exit interface. Okay, so there are level 1 routes that can be ultimate routes. There can also be level 1 routes that are not ultimate routes, that are parent routes. We'll talk about those in a second. So you've got an ultimate route, has a next hop IP or outgoing interface. A level 1 route has a mask equal to or less than the classical mask. And you have a level 1 parent route. That is a route that has been subnetted, a network that is subnetted. Level 1 parent routes are not ultimate routes because level 1 parent routes have routes underneath them. So here we see 172.16.0.0/16 is variably subnetted, 5 subnet string mask. This is a level 1 parent. It does not have a next hop. It does not have an outgoing interface. So that is just a level 1 parent. It is not an ultimate route. Below this, you can see routes that are child routes that are ultimate routes, and they are layered level 2 child routes. And they are the routes underneath a parent route. So when we start looking at the routing table, we can see, all right, here's the parent route, 172.16.0.0. Here are the child routes. Well, the level 2 child routes are ultimate routes because they're always going to have an outgoing interface. This was very important in the past, and it's still important, but it was very important in the past because it used to be when you didn't have a default route, if you went into a hierarchy, in other words, if I went down into this hierarchy and jumped in here and started looking at the child routes and did not find a child route, it used to be that if the router was not performing classless routing, it would not go back out and try to find a default route, okay? But now today it will. So if you've got a level 1 parent and level 2 child routes and you don't find a max, so say 172.16.5.1 come through here and was trying to go through, well, let's say 10.1, to make sure I'm not jumping in anything. All right, 20.1, get it way out there. Then it would not have a route and it would have to come all the way back out to find this default route. Today, we don't have to worry about that quite as much because it will come back out. We just have to make sure there is a route. What do you think is going to happen if there's no route in the route table and there's no default route set? What is the router going to do with that packet?
It will be discarded.
It's going to discard it, exactly. It's going to put it in the bit bucket. It's going to discard it and get rid of it. If there's no path in the route table, that packet is discarded, okay? So be aware of that. Here are some child routes in the hierarchy. Here's a parent route and then a child route coming down in here, okay? So you see this is 172.16.0.0, and then these are child routes. And notice they're ultimate routes because they do have a connected interface. So these are level 2 child routes and ultimate routes. So 0.0.0 right here in this route table. What kind of route is this? It's going to be a level 1 route. Okay. 192.168.3.0. Let's see where that sits. 192.168.3.0. Directly connected, fastnet 0.0. That's a level 1 route. 192.0.2.64/26. Let's see here. Okay, well this is here's the parent route. Okay, and so this 264 is under this parent and it's part of that network. It's a subnet of that network. So this is going to be a level 2 child route. Question for you: is that an ultimate route or not? 192.0.2.64/26. Is that an ultimate? Level 2 child ultimate? The answer is yes, because all level 2 child routes are ultimate routes because they have either an outgoing interface or an ex-hop IP address. How about this 2.0/30? Also level 2 child, and then this level 1 parent is here. Woohoo! Got it right. It's important to kind of know these, just know how the route table works, how the routes are in there. It is hierarchical, and you can look. The first thing it's going to always try to do is match a level 1 route. Okay. If it matches level 1 ultimate route, it's going to use that. It will use the longest match of a level 1 ultimate route. If it doesn't match any of a level 1 ultimate routes, it'll look for a level 1 parent route, and then we'll check in the child routes to find a route. If you are running classless, which you should be, it will then, if it does not find anything in the child routes, it will then come back out and check for a supernet or a default route. Okay. If you've turned off classless, so you put no IP classless for whatever reason, it would not come back out. But we don't do that in the real world. I think they have you do it in the lab just to show you how it does it. The longest match in the route table wins. So if you've got multiple routes and you've got a packet that's coming through, the one that matches the most number of bits will be the route that gets used. So even though all three of these routes may match this 172.16.0.10 destination packet, only the one that has the longest match will be used to forward the packet. Very important. Leftmost bits, longest match. Now, IPv6 works exactly the same, folks. We do use our RIP-NG, which is a new, little different protocol. We had to use show IPv6 route to CRV6 routes. Okay, and it's got the same directly connected routes, metric, all those items that are the same. So no different there as far as the way things are shown. The route source, outgoing interface, directly connected metric. So remote entries for IPv6, same as before. Route source, next hop, route source destination, administrative distance, metric, next hop, and the outgoing interface. Notice the next hop is a link local address. Now, that's it. That is chapter 3, dynamic routing with RIP. You got some labs to do, and then we go into looking at switch networks in our next chapter. Are there any questions? I'll stop sharing my desktop.
Kelly.
Yes.
Yeah. I checked chapter 4. There are no labs. Is there any reason for that?
Yep. Because when you look at chapter 4, there are no labs. There are no packet tracers for chapter 4. Yep. Okay.
But what about real labs?
There are none that I'm aware of inside of
NetLab.
NetLab's correct.
Yeah. Okay.
So chapter 4 in this new version does not have any labs in it. So it's just teaching you how to do basic switching.
Okay.
So any other questions? So yeah, you got it pretty easy this week. Be a good time to get ahead, right?
Yep.